but I cannot find the slide. Capture slide on second.
On Slack, if you look in general, I just posted them.
Oh, got it.
Yeah, so sorry, I need to, my authentication for GitHub has expired. I need to fix it. I will, but not. That takes a few minutes and it's not worth doing right now. Okay, so let's talk about today. This is actually probably my favorite lecture of the semester. My favorite unit is the second unit of probability. So we did the kind of basics of probability theory last time, but now we're going to extend it to talk about random variables, right? And I think random variables are a really cool concept in statistics that help us think about uncertainty as a kind of knowable thing, rather that help us think about uncertainty as a distribution. So let's talk about what a random variable is first. A random variable assigns values to events. So my mask goes upside down. Random variables assign values to events. So for example, sorry, let's get to the definition. So a random variable takes an event and affixes a value to it. Each value within that random variable must be mutually exclusive, right? Meaning there's no overlap in values. The set of all values must be exhaustive for that random variable, or what we've called the sample space, omega. That is, any possible value in the sample space must be possible to be assigned within a random variable, right? Everything that's possible within the sample space, the random variable must be able to map as an event. And discrete random variables, we have two kinds of random variables we'll typically be thinking about. Discrete take on a finite number of values, like a binary takes on values of true or false, or 0 or 1. But these could also be categorical variables that take on labels like blue, green, yellow. They could also be integers, right? 1, 2, 3, 4, 5, 6, as opposed to a continuous variable that takes on an infinite number of possible values, and those values are real numbers, meaning they include non-integer values, right? So when we say a discrete variable, we can mean everything from a binary to a categorical to a count. A count variable is typically, we can think of as a non-negative integer. That is, it can take on 0, 1, 2, 3, but it only occurs in whole numbers, integers. So discrete variables take on a lot of different shapes. Continuous variables are real numbers. So those can take on any numeric value. So the simplest random variable we work with in statistics is the Bernoulli. The Bernoulli is just a fancy way of saying binary. It's the distribution we use to represent a binary variable. So any random variable with two values can be called a Bernoulli random variable. Bernoulli variables are typically represented either as 0, 1 or true, false, but they could be a two-label categorical. So in your homework, looking at the survey data from China and Mexico, China-Mexico was a two-value, right, variable, and that could be treated as a Bernoulli random variable. So let's think about working through a Bernoulli. We can think of a coin flip as a discrete random variable x. What are the possible outcomes for x? Yeah, heads and tails, right? Top and bottom. 0, 1, however we want to code that. We have two possible outcomes. And so the sample space omega contains heads, tails. Both of those are possible to observe. Those are mutually exclusive. You can't be both heads and tails, right? So it fits our definition of the random variable. Now the random variable is going to be the coin flip. That's going to be our experiment, but that's going to generate some value x, right? Each time we flip the coin, it's going to generate a 0 or a 1 every single time we flip it. So that coin flip acts as a data generating process, which is a random variable that produces binary data, right? So we can treat that coin flip as a discrete random variable. The coin lands on heads, we'll call x equal 1. If the coin lands on tails, we'll call x equals 0. And we can define the probability of a Bernoulli random variable as the probability of success or the probability of a 1. Now that's arbitrary because P of x equals P equals 1 minus, right, or P of not x, sorry. And then P of not x equals 1 minus P. So once we've defined the probability for success in a Bernoulli, we've also defined the probability of failure because there's only two possible outcomes, right? So the probability of success is P, the probability of failure is 1 minus P. So we can say P of x equals 1 is equal to P. And here is some fancy notation that we're going to start to use more and more frequently. We're going to say that x is a randomly distributed variable. That's what the tilde means here. We're kind of using a statistical distribution notation. So we're saying x is a random variable that follows a Bernoulli distribution with probability of success P. That's how we read this. We say x is a random variable that follows a Bernoulli distribution with probability of success P. We're going to see this notation more and more for different kinds of probability distributions. I want us to get used to it. But effectively what we're saying is any value of x can be realized by computing a value from a Bernoulli with probability P. I'm going to, because Bernoulli is kind of a weird word, I'm just going to flip back for a second to make sure we're all on the same page. We can define, so we're talking about probability distributions today, y'all. And you're going to hear me say the word Bernoulli way too many times, but Bernoulli just means binary. So if you hear me say binary, a random variable with two values is called a Bernoulli random variable. So when you see the word Bernoulli, just know that we're saying two values, binary. The slides are on Slack, by the way. I was not able to load them to GitHub. Okay, so x is a randomly distributed, a random variable that follows a Bernoulli distribution with probability P. So we name the variable x. Note that it is randomly distributed. That's what the tilde sign means. It's randomly distributed. It follows the Bernoulli distribution. And the Bernoulli distribution only has a single parameter, and that's P. Some distributions have more than one parameter, but Bernoulli only has one, and that's probability of success. Because we only need two numbers for determining a coin flip, right? We need the probability of heads and the probability of tails. But to compute the probability of tails, we just need 1 minus the probability of heads. So we actually only need one number to understand the probability of any events x equals 1. Okay. So let's flip some coins and look at the Bernoulli distribution. When you're doing random work with simulation or random numbers in R, if you want your work to replicate, you need to set a random seed. And that just tells your computer to draw random numbers in the same way every time. Otherwise, it will use a different seed and generate different results. And that's okay. On average, they'll work out to be the same. That's called simulation error. But if we want it to come out the same every time, set a seed. You can use that with set.seed. I'm doing 1, 2, 3, 4, 5. It's arbitrary. You could set any number you like. Now, what I'm going to do is I'm going to take a sample of coin flips. In R, we're going to call the Bernoulli distribution. The Bernoulli distribution is a special case of the binomial distribution. So we'll sample from the random binomial distribution. We'll take random draws from a binomial distribution. We're going to take 5 coin flips, and we're going to do one coin flip for each of those 5 trials. And the probability of success is 0.5. So here's what the R binom code arguments we're giving it. R binom, we're saying how many trials do I want? We're saying how many flips am I going to do? We'll call that I equals 1, and then what probability does it take? Actually, so we're going to flip one coin 5 times. And each time it has a probability of success of 0.5. Now, what we're going to do when we flip those 5 coins is we're going to get back a vector that tells us, let's actually just like look through this code. It's a little easier. Let's walk through that way. Here we go. So if we run just this code R binom, here's what we get. We get 5 coin flips. It is 2 zeros and 3 ones. And our table here showed us that we got, well, that was on a different run. But if we run this again, and then we look at the object sample of flips, in this case, we got 4 zeros and 1 1. 1, 2, 3, 4 zeros, 1 1, right? That's what our table shows us. So we are using simulation to flip coins, right? That's what a Bernoulli random variable is, and we can use R using the R binom function with a sample size of 1 to generate a Bernoulli variable. So if you ever need help remembering how the R binom function works or any other of the probability functions, you can go in here, R binom. So it calls the I parameter size, right? But that's how many coins is it going to flip in each trial. N is how many iterations are we going to do of the sampling. I is how many times do we sample the event each time we run an iteration. And prob is just the probability of success. Okay. So this is the result of taking 5 draws from a Bernoulli with probability 0.5. In this case, what we have on the slide is we got 1, 0, and 4 ones, right? Every time we run it, we're going to get something different. Now, maybe we want to think about how likely am I to observe different kinds of values, right? So how likely am I to, for example, observe a 1? This is going to be more interesting as we get to different kinds of random variables. But I want to introduce 2 sort of new concepts. One is a probability mass function, and one is a probability density function. So we have PMF, probability mass function, and PDF, probability density function. So we're going to use the probability mass function to show how likely each value is in a random variable. So the PMF of a variable X is defined as the probability that a variable takes on a specific value of X. So this is quite easy for the Bernoulli, right? The PMF for X equals 1 is just P. The PMF for X equals 0 is just 1 minus P, right? But this probability mass function has to define values for the entire range of possible values in omega. So these PMFs get more complex when we get to more complex distributions. But in this case, it's quite simple. The probability mass value of X equals 1 is going to be equal to P at X equals 0 is going to be equal to 1 minus P. And in R, you can use the P binom function to get the probability mass for a binomial. Let's see, what's the probability of 1 with a size of 1 and a P of 0.5? Not quite. Is that, oh, because I always get them confused. I think it's actually D binom. Yeah, so it actually uses D binom for the probability mass function and P binom for the cumulative distribution. We'll get there. We'll get there. Don't worry about it. or through those functions. I get them confused all the time in my head in terms of how R labels them, but it's okay. Here's the probability mass function for our coin flip. At 0, we have 0.5 probability. At 1, we have 0.5 probability, right? That's pretty easy. Here's the probability mass function for passing the bar in New Jersey, right? About 65% of test takers take the test. So if we randomly sample one test taker from all test takers, we have a 65% chance of observing a 1 and a 34.7% chance of observing a 0, right? So binaries can take, they don't have to be uniform at 0.5, right? We can have different values of P. We can also think of the cumulative probability distribution, right? So we have the probability mass or probability density function. We also have the cumulative probability function. The reason you'll sometimes hear probability mass versus probability density is because for integers, we typically call it a probability mass. For continuous variables, we'll call it a density. But here we can also talk about the cumulative probability of an event. So how likely is a variable to take on a value less than or equal to a specified value? This is a very different question. Rather than asking how likely, if we were, say, on a continuous measure, what is the probability that x equals 2? Is one question that we ask with the P and F question. With the C, D, F, the cumulative density, we'll call it cumulative mass just to keep it standard for now. We'll ask, what's the probability that x is less than or equal to 2? Right? So we're asking very different questions. The PMF asks, what's the probability that x is exactly equal to 2? The CMF, the cumulative mass function, asks what is the probability that x takes on a value less than or equal to 2, which effectively sums up all the probability mass under 2. And we can see that here in the formula for the probability mass, or the cumulative probability function, the CDF, right? Cumulative density or cumulative mass. We're going to sum over each value of k, where k is less than or equal to x, of all probability mass values, right? So in our case, for it's pretty uninteresting for a Bernoulli, right? The P so the probability mass function here for 0 is what? 0.347, right? The probability mass for 1 is 0.653. The cumulative mass for 0 is still 0.347 because it's just all values equal or less than 0. And the probability mass for 1, though, is what now? Is 1, right? Because we have to sum 0 in it as well. So the probability that you will take on a value less than or equal to 1 is always 1 in a Bernoulli random variable. Now we can see that this definition will get more interesting as the potential numbers of values of k increases, right? So for variables that can take on more than 2 values, this becomes more interesting. The CDF always ranges from 0 to 1. Okay, the cumulative density function always ranges from 0 to 1, and it never decreases as x increases, meaning it always goes up. Probability cannot go down, right? As we move along a variable x, it always increases, right? And of course, the probability of an event ranges from never happens to always happens, 1 representing always happens, 0 representing never happens. So the minimum value is always 0. The maximum value is always 1. And a cumulative density function always sums to 1. It must sum to 1 by definition. That is, if we have a random variable, something in the sample space will happen, right? Something in the sample space must happen. Okay. So I want to introduce kind of as we push this forward, we're going to get to normal variables by the end of the day. And that's something that we're going to work with a lot, but I want to introduce a few other kinds just to get us kind of thinking about how these work. A uniform random variable is a special kind of variable, and it's a continuous variable that takes on values, any real numbers on some interval a, b, right? So a and b are two numbers that represent the cut points for our uniform random variable. And between a and b, this distribution says any number in that range has equal probability of being observed as a realization of the random variable. So X uniform 0, 10. Now we have two parameters, right? So how would we read this off? We remembered how to read the Bernoulli, right? We would say X is a randomly distributed variable that follows a uniform distribution that begins at 0 and ends at 10. So let's think about what this might look like. One way we can think about the shape of a distribution is to simulate it, right? We can do a Monte Carlo simulation and just like look at what it looks like when we draw a lot of numbers. So I can use R unif to draw random numbers from the uniform distribution. You'll notice a pattern. There's R binom, R unif. We'll also see R norm. All of those are our random samplers, right? So we want to draw random numbers from a particular distribution in R. We use an R and then the name of the distribution. So in this case, it's usually an abbreviated name, but R unif will draw random numbers, 10 random numbers in this case, n equals 10, where the minimum value is 0 and the maximum value is 10. And here are the 10 numbers I drew on this sample, right? 1.6, 3.2, 5, 7, 9, 0.34, 1.5, 7.3, 0.11, 3.9, right? All over the place. And this is the shape of the histogram. It actually does appear to have a little bit of a shape, but we have a small sample size, so we probably don't want to draw too many conclusions from that, right? It's only 10 draws. So let's move it up to 100. Let's see what happens. We still see a little bit of a shape to it, but let's keep going. This is at 1,000 or 10,000 rather. And this is actually very close to the shape of what a uniform distribution looks like. A uniform distribution should be flat. The probability mass of a uniform distribution should be perfectly flat over the sample space. So in this case, our theoretical distribution looks like that on 0 to 10. Now, you'll note that the density, the probability density here is 0.1. Of course, it's a little fuzzier when we get to continuous variables because we don't actually have a 10% probability of drawing 5.0922, right? But it just assigns that as a flat probability across the entire distribution. The math works out even if it looks a little funky to our eyes. But we have a uniform probability of drawing anything in the sample space, right? High values are just as likely as low values, are just as likely as values in the middle. When we see a distribution like this, or like this, what it's telling us is that any value in this range is equally likely to occur. There's no tails, there's no mode where we see a peak, right? It's perfectly flat. Here's the math for it. I'm not going to be too worried about it, but we can define the probability of drawing any value as 1 over b minus a, where b and a are the cut points, right? And then we can formally define the PDF as 1 over b minus a for all values that belong to the interval AB, and 0 if it's outside the interval AB, meaning we never observe anything in a uniform random variable that is outside of our interval, right? The CDF is going to look a little different. So let's think about what the CDF looks like. This is the PDF, the probability density for X uniform 0, 10. And this is the theoretical one, right? So let's look at what we have here. Again, we have that line from 0 to 10. But I wanted to illustrate what's the likelihood of us drawing a 12. What's the likelihood of us drawing a -2? 0. Absolutely zero, right? We have a fixed probability of drawing numbers in this range, and we have no chance of drawing anything outside of that range. Questions? The uniform is pretty easy. Sorry, slow me down. I know this is like heavy conceptually, so please slow me down and ask questions. Okay. This is what the cumulative distribution function for X uniform 0, 10 looks like. So let's think about how we get from here to here. What's the cumulative likelihood of observing a 1? Meaning something less than or equal to 1. Well, we can just sum up each of these values, right? And when we sum up all these values, as we keep going, the line is going to increase uniformly, right? Because each value has equal probability of being observed. So what we're going to get is a straight line for the cumulative density. That is, we have a 100% chance of observing something between 0 and 10. And we have a 50% chance of observing something between 0 and 5. So we can use this CDF to map off the probability of observing something less than or equal to a particular number. So 7.5, 0.75 probability, right? So if I were to draw a random number from a uniform 0, 10, there's a 75% chance it will be less than or equal to 7.5. For those of you who have done a little calculus, this is the integral of the probability density function. The probability density is the derivative of the cumulative distribution function, meaning this curve, let's kind of go back over here. Remember that an integral represents the area under a curve, the area under some graph. So in this case, our graph is like at 0, at 0.1, and then again at 0, right? So as we think about moving from, say, 0 to 1, we can compute this proportion of the area under this line, right? Now, as we move, maybe if we take very small steps, we'll note that, okay, so at 1, we'll say that our probability should be at 0.1, right? Then we move out to 2, creating this additional area. Our probability will move up to 0.2, right? And we'll notice that we get a straight line as we move up the probability mass function, and we start to add up these areas under the probability curve. We'll end up with a perfectly straight line. So to obtain the cumulative distribution function, we sum up all possible probabilities from 0, or from a starting point to an end point. Or in terms of calculus, we take the integral of the probability density. And we could also see that if we take the derivative, right, at any point here, we'll flip back to the probability density, right? If we take the rate of change of the slope at any point here, the slope is constant, right? The slope is not changing here. So the derivative will result in a straight line. If the calculus is not working for you, that's fine. Just remember that we're adding up the probability. And as we go across a rectangle, as we sum up each block of it, the line gets bigger and bigger. The line goes higher and higher in a constant way, right? Because each block has as much mass as the block preceding it. So we're going to get a constant increase in cumulative probability. So that's what a cumulative probability distribution is. The CDF the maximum value of it will always be 1. The minimum value of it will always be 0. It can never be higher than 1, can never be lower than 0. And we'll see that it has to go up as we go across. It can never go down. It could stay flat, but it can never go down, right? So as we go, we can't have negative probability, right? And the reason why it can never go down is that probability, we can never have a negative possibility that an event will occur. That doesn't make sense. So the only thing we could observe here is a 0 probability or a non-zero positive probability, right? And so if we add up sequentially, moving left to right from one point to another, the cumulative probability, meaning the total from one point to another, must increase or stay flat. It will never decrease. Okay, so a CDF for a discrete variable is the sum of all probabilities for values x less than or equal to x. So that is, we'll see this more with the binomial in a second. We'll come back to a discrete variable where we'll get to work with this a little more closely. When x is continuous, we can't actually sum each of those values, right? Because like, how many possible values are there here? It's, we have 9.89736. There are an infinite number of possible values between 0 and 10. So we can't actually sum up every possible value, but we can take the integral, which is the equivalent for a continuous measure. So we can take the integral from a to b or negative infinity to x, if we're going to just generically define it, right? For a uniform, it's a to b because everything that's less than a is automatically 0, right? But we can take that integral to get the cumulative density. Okay. Probability density. What does that do? What does a probability density function tell us? What does the probability density function tell us? It's the probability of observing one event, right? So it's going to do experiment, let's say the probability of eating pizza for me today. Probability pizza equals 1. Call it a 0.4. Okay, so what is the, and we'll call this variable pizza. So what is the PNF for pizza equals 0? What's the instantaneous probability that pizza equals 0? 0.6, right? And what we could call it the instantaneous probability. Effectively, we're just asking what's the probability of the event. When we ask what's the probability of mass. What about that? 0.4. Now, what is the cumulative probability that pizza equals 0, which another way of writing that is to say it's less than or equal to 0. Again, it's 0.4. I'm sorry, it's 0.6. Right, we have 0.6 chance of observing a 0 or something less than 0. Something less than 0 doesn't exist. So it's just the probability of observing 0. The cumulative probability of observing pizza less than or equal to 1. What? 1. So when you think about the difference between the cumulative and the probability mass and the cumulative mass, the real difference is we're asking equals or less than and equals. That's the real difference between the two. Cumulative, just think of it, it adds it up, it sums it all up, right? Sums up everything beneath it. We feel okay about that? Okay, so when we repeat Bernoulli trials many times, we get a binomial random variable. A binomial random variable is a sum of binary events. So a Bernoulli random variable is a sum of binary events. If I were to ask you all to take the bar exam in class right now, right, I could take random samples of groups of 4 students and ask them each to take a test. And then I could sum up the number of people that passed the test. And that would be a realization of a binomial with 4 trials with some probability of success, whatever this probability of passing the test is. So when we repeat Bernoulli trials many times, we get a binomial. So binomials are counts. They are integers. The lowest value they can take is 0. The highest value they can take is the number of trials, right? Because the values of each individual trial will be 0 or 1. So it'll take on some value between 0 and k. We typically call k the count of the binomial trial, right? We have a fixed number of trials, right? And so k is the maximum, 0 is the minimum. A binomial random variable is the sum of n, here's some new terminology, independently and identically distributed Bernoulli random variables. What do we think that means? Independently and identically distributed.
They're not affected by other trials.
That's exactly right. So the independent part means the outcome of one event is not dependent on the outcome of a prior event, right? That is, what happens next does not depend on what came before. So that's the independent part. What about the identically distributed part? Here, think back to a random variable can be random, a variable can be randomly distributed following a Bernoulli distribution. And what parameter does it take? P, the probability of success, right? All Bernoullis follow this parameterization. With a single parameter P. So identically distributed means they follow the same probability distribution. They do not depend on each other, and they all follow the same probability distribution, meaning they all have the same probability of success in this case. But independent and identically distributed means 2 things. It means the outcomes do not depend on each other at all. They're independent of each other. Another way to think about that is learning one outcome doesn't tell us anything about the next outcome. And they're identically distributed, meaning they all follow the exact same probability distribution. In the case of a binomial variable, that means every single trial follows the same Bernoulli distribution. It's a binary event with fixed probability P. The P does not vary across trials. That's what IID means. So if you see IID, it means no dependence and same probability of event. So a binomial is just when we add up lots of Bernoullis, but they're all the same Bernoulli, right? They have to come from the same distribution and they have to be independent of each other. So binomial variables take on integer values between 0 and here I should actually say k, where k is the number of trials we're going to run. But we could say n, right? Okay, so let's imagine we flipped the coin 5 times and then repeated the exercise twice more. So we're going to sample x from a binomial distribution where n is equal to 5 and p is equal to 0.5. So we're going to get 5 coin flips, 0, 1, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0. So what would this realization of the binomial be? What value would it take? We take the value 1, because we're just going to sum up the vector. Here, again, it would take the value 1. What about this third one? What value would that take? It would take the value 4. So for these three draws of the binomial, NP, binomial 5, comma 0.5, we observed 1, 1, 4. And we can see that this is just 5 coin flips for each one, right? But then instead of reporting out each coin flip, we're going to sum the vector, and we're just going to report a single value, just the integer. We lose information here. What information do we lose when we sum it? If I just tell you 1 and 1, are these identical vectors? We lose the order, right? When we sum it, and when we use a binomial, we lose the order of the Bernoullis, right? It's irrespective of order. We may be really interested in order, but using a binomial framework, we don't preserve that information because we're just going to sum over the whole vector. This and this are indistinguishable as binomial outcomes, even though as Bernoulli outcomes, they're different, right? Okay. So X for each trial, again, 1, 1, 4. Here's the probability mass function for X is binomial 5.5. So this looks really different, right? Before, when we said the Bernoulli, what shape did it have when we were looking at Bernoulli 0.5? Flat. Both had a 0.5, right? Now we are nowhere near that, because we're looking at the sum of 5 Bernoulli events. So we have much lower likelihood of observing a 1 than we do a 4. So what is the most likely event according to this probability mass function? When we look at this graph, what's the most likely event to occur? X is equal to 2 or 3. Those are the most likely outcomes. We have about a 33% probability of observing either a 2 or a 3. We would call those the modal values in this distribution, the modes of the distribution being the most frequent. The mean of this distribution will be 2.5, but of course 2.5 can't actually be observed, right? Because it only takes integers. So let's turn this into a cumulative function. First, let's read it off as a probability mass function. Here, we're at like, yeah, less than a 5% chance of observing a 0. So it's very rare to observe a 0. To observe a 1, 15% chance of observing a 1. Observing a 2 and a 3 both have about a 33% chance. Observing a 4, we have about a 15% chance. Observing a 5, we have about a 5% chance. So it's symmetric, right? We can see that this distribution is symmetric when p is equal to 0.5. It won't always be in a binomial, but in this case it is. That is, if we cut it here, the left-hand side and the right-hand side, if we cut at the middle, look exactly the same. So let's think about doing this as a cumulative density, right? So recall that to obtain a CDF of X less than or equal to, I don't know, let's say 4. What do? We sum over 0 to k, where k is going to be our cut point, the probability mass of k. So we're going to take all probabilities k
on some range 0 to p. So let's compute the probability mass for 2. And we can round. So what do we want to call 0? Call it 0.05. Yeah. We'll say p of 0 equals 0.05. P of 1 is what? 0.15, sure. Rounding is good. P of 2 is 0.3. Good enough. So the PMF, or the cumulative, we put 4 here, so let's change it to 2. Then we observe a value less than or equal to 2 is what? 0.5 plus 1.15 plus 0.3. So we obtain a value that's approximately equal to 0.5. Actually, it'll be exactly equal to 0.5 here. But our rounding did not hurt us. Right, so we have a 50% chance of observing a 2, 1, or 0. What about if we go up to 3? We need to add another 0.3 to it. So the C, D, F of x less than or equal to 3 is equal to 0.8. 80% chance of observing anything 3 or lower. Yeah. So this is the easiest way to think about going from the probability mass to the cumulative density, is to envision a binomial. And then all you're doing is adding up each of the bars, adding up each of the possible values in that distribution, and you'll get right there. And this is what that cumulative distribution looks like. We can't observe values that are non-integer. So technically these would just be points, right? But, well, no, they wouldn't, because the probability of observing anything less than or equal to a 0 is 0. The probability of observing anything less than or equal to 1, or less than 1 rather, is the probability mass for 0. The probability of observing something greater than or equal to 1, but less than 2, is the sum of 0 and 1 on the probability mass, etc. Right? It takes a stair step, but we can see it's kind of nonlinear, right? We get a big jump here, but as we get over here, this last step is really small, right? These steps are quite large, going from 2 to 3, and that's because those bars are quite high on the probability mass, right? So we're getting big jumps as we go from like 0. If we go from negative to 0, small jump, right? 0 to 1, larger jump, right? A jump of about 0.15. We go from here though, it's going to jump up by 0.3. As we go here, it's going to jump up by 0.3. If we go here, it's going to jump up by 0.15. And as we're going to go here, it's going to jump up by 0.5. But at the end, it must be at 1. By definition. We will observe something between 0 and 5. The chance of observing something less than or equal to 5 is 100% if you flip 5 coins. Right? You can't observe something greater than that. And 0 is a possibility. So yeah, you're going to see something in that range. That's the cumulative distribution function for the binomial 5.5. So let's move on then to the normal. And this is one that we're going to spend the most time working with as we kind of get through regression. We'll come back next semester when we talk about generalized linear models to logistic regression and other kinds of regressions to the binomial distribution, but we'll primarily be working with the normal for the rest of this semester. So the normal distribution, sometimes it's also called the Gaussian distribution. So you may hear it called Gaussian, but it's that's the same thing as normal. So if you hear someone say Gaussian, they mean normal. So that distribution is continuous, and it takes on values from negative infinity to infinity. The normal distribution always takes on values range from negative infinity to infinity, no matter how big or small that distribution is. The possible values on it are always infinite. It has two parameters, unlike our, we've seen four distributions so far. Bernoulli had one parameter P. Uniform had two parameters, start point, end point, A and B. Binomial had two parameters, N and P, the number of trials and the probability of success. The normal has two parameters, mean and standard deviation. And these define the shape and location of the distribution. Mu determines where the distribution is in terms of its center of mass. Sigma, or the standard deviation, determines how spread out it is, how peaked or flat it is. So we call the mean mu, right? That's mu. This is sigma, and that's the standard deviation of the normal. Sometimes you'll see it represented as sigma squared, and that's the variance. The variance is simply the square of the standard deviation. Sometimes you'll see it written out both ways, but they can be equivalent, right? We can always take the square root of a variance to get back to the standard deviation if we want to work on those terms. So here are three normal probability densities. The red curve is a normal distribution with mean 0 and standard deviation 1. The mean 0 means it is centered over 0. Normals are always symmetric. Their left side and right side always have the exact same shape. So in this case, our normal is centered over 0. And the shape is the same on both sides, right? We have this slope going on both sides. This has a standard deviation of 1. Now let's compare that to the green one. The green one also has a mu, or a mean of 0, centered at 0, but it has a standard deviation of 2. So let's look at those different shapes. So first, obviously, the red is taller. What do we think that indicates? This is a probability mass, so what does it indicate? To have a higher value at 0. A higher probability of what? Being close to the mean. When that peak is higher, you have a higher probability of observing a value in that range. The higher the peak on a probability mass, the higher the likelihood of observing that value. So for the red, we actually have a higher likelihood of observing the mean on this distribution than we do on this distribution. Can someone remind me what the standard deviation is? The definition of it? Yeah. From the mean. How different on average is a single observation from the mean? So in a distribution where each observation is 1 different on average from the mean, we're going to observe the mean more often than we are in a distribution where the average observation is 2 different from the mean. It's going to be more compact, right? A lower standard deviation means a more compact distribution. And because these distributions always have to sum to 1, if we squeeze that mass in, the point goes up, right? Everything under here on all 3 of these curves sums up to 1, right? By definition, has to do that. So on this red curve, the mass of the distribution is confined. So let's think about this for a second. This is probability, right? What's the probability on the red curve of observing a 5? Read off on the graph. Nearly 0. Now remember, this goes out to infinity, right? So I could go over here to 276. What's the probability of observing that? Nearly 0. It's not 0 exactly. Could happen, but it's nearly 0. Indistinguishable from 0, right? Okay, now let's look at the green curve. What's the probability of observing a 5 on my green curve? It's hard to read, but let's call it a 0.02. Much higher, right? So what we get when we increase the standard deviation is we push down the center of mass. We go from here to here, right? We just push it down and spread it out. We're spreading the probability out over a larger space. More events, a bigger range of numbers are possible under the green distribution than the red distribution. It has more spread. We could see a higher range of values occur. We are more likely to see a higher range of values. This distribution tells us that, you know, you could draw anything reasonably from, like, we kind of look at these tails to think about the tail as it gets close to 0 tells us the events that are very unlikely to occur, right? So this tail, we'll say, is getting close to 0 at -5 and close to 0 at 5. So we have a pretty good chance of observing something between -5 and 5, right? On the red curve, the tail's getting close to 0 at closer to like 3, right? 2 or 3. And so here, the range of likely values we'll observe is much lower. It has a lower spread, it has a lower standard deviation, right? So the lower standard deviation means less spread to the data. Lower standard deviation means a higher peak. Higher standard deviation means a flatter peak. Squish that normal down, right? You either pull it up or squish it down. Now, so we're okay on standard deviation idea that we can kind of make it more peaked or more flat, depending on how high or low the standard deviation is. And again, the standard deviation can never be less than 0. A standard deviation of 0 just means it's a single point, right? It never varies from the mean. Okay, so let's move mu. We moved the standard deviation. What happens when we move mu? So if mu is 2, we move the center of this distribution over on the x-axis by 2. And now, instead of 0 being the most likely value to observe, 2 becomes the most likely value that we will observe. Effectively, all we do to move mu is we add 2 to every single value of the red curve. We just push it over. We move the location. These two curves have identical shape, blue and red, right? Because they have the same standard deviation. The only thing that's different about them is their location on the graph. So if we add 2, we just shift it over by 2, same exact shape. So mu, when we say that the mean tells us the location of a normal, we mean that quite literally. It tells us where on the x-axis it will be centered. Mu tells us the central point. It tells us the mean of the normal distribution, and the mean of the normal distribution is always its mode, which means its highest point. The mean of the normal distribution is always the highest point of the curve, and the mean tells us where that curve will be centered. The standard deviation tells us how spread out the curve will be from the mean, how peaked it will be at the mean, and how spread out it will be away from the mean. If you ever hear someone talking about tails on a distribution, we could talk about, let's go back to the green and the red for a moment. The green distribution has larger tails than the red distribution. And what we mean by that is that events that are, we might call them extreme events, that is, events further away from the mean, are more likely to occur on the green distribution than the red distribution. One way we can tell the likelihood of observing an extreme event, that is an event that's far away from the mean, is by looking at the width of the tails. If we have wide tails, we have more likelihood of observing an event that's very far away from the mean. If we have narrow tails, we have very low chance of observing something far away from the mean. So if you hear people talking about tails of distributions, that's what they're talking about. How likely are we to observe something far away from the mean? If it has large tails, we are likely to observe something far away from the mean. If it has small tails, we are unlikely. Sometimes they'll call them fat and skinny. We could use large and small, it doesn't really matter. But the tails tell us how much probability mass is there far away from the mean. Now, let's look at this as a cumulative density. So we're going from this curve, right? This is our typical bell curve, our normal curve. And now we're going to take the integral of it. We're going to sum up all values from negative infinity to each possible value as we go. And this is what the normal CDF looks like. So let's stick with our red one for a moment. The cumulative probability of observing something -5 or below on the red is basically 0. But then we get to the mean. The cumulative probability of observing something less than or equal to the mean on a normal distribution, it's going to be 0.5. Right? So in this case, the mean is 0. We have a 50% chance of observing something less than or equal to the mean. Notice how quickly this rises. Notice how quickly the CDF rises. And that's because we have a really steep increase in probability throughout this whole range, right? So that steep increase in probability is going to lead to a really steep increase in cumulative probability. We can see this curve is actually symmetric too, right? We have a kind of S-shaped curve that takes on the same shape on the left and right-hand side of the distribution. It asymptotically approaches 0, going toward negative infinity, and asymptotically approaches 1, going toward positive infinity, meaning the line pushes toward 1 but never quite reaches 1, because there's always more extreme values that are possible under a normal, right? It ranges from minus to positive infinity. So we could observe anything, but we have effectively 100% likelihood observing something less than or equal to 5 with our red normal. It's not actually 100%. It's like 99.99999, right? But we're pretty darn close to 1. So this is the shape of the normal cumulative density. Notice the same thing here. Our green normal, that is the one with the higher standard deviation, the probability accrues less rapidly. So the slope here, right, it starts a little slower, and then the slope of it is a bit shallower, right? On the red, it starts to rise later, but it rises quite quickly, right? Here, we're going to start to raise around -5, because we observed that there is a probability of observing events there, right? So we're going to start to increase there. It's going to increase a bit more slowly than the red. It will still hit 50% probability at the mean though, right? We'll still have a 50% probability of observing something less than or equal to the mean, but what counts for less than or equal to the mean here has a very different range. Yeah? Okay. If we take the blue curve, we're just moving the mean over to 2, right? So now we're going to get to 50% probability when x is equal to 2. But the curve will have the exact same shape. You can see this is parallel at each point to the red curve, right? The shape is identical to the red, other than its location. Meaning if we were to take the slope at each of these points, the slopes would be identical. We feel okay about this? Questions? Ask them. It's okay. The slope, well, okay. So, sorry, on the CDF. So the slope is just the rate of change of the cumulative probability here, right? So it's just how quickly is the probability changing at this point. And as the slope approaches 0, the probability stops increasing, right? Here, as the slope approaches 1, that means as it gets closer to a vertical line, it's increasing very quickly, right? So this has a very high slope in this region, right? The probability in this region is increasing incredibly quickly. The probability in this region here is increasing a little less quickly, and we can see that over here because the slope of this line is both shallower and slower, right? And wider. So as the line becomes increasingly vertical, that means we're closer to 1. As the line becomes increasingly horizontal, that means we're closer to 0, meaning no change in probability. A vertical line means this event is guaranteed to happen. This is tough to get your head around, but I think being able to understand visually what these mean is really important to grasping some of the more advanced stuff we're going to do in statistics, right? The idea is that we have probability over here and our values of X over here. And as we see a curve, usually we're not going to be looking at the CDF. Usually we're going to be looking at the PDF. But when we look at a curve like this tells us a tremendous amount of information about a variable. This tells me virtually everything I need to know about a variable. If I can make a plot like this, I can tell you how likely a whole range of different values are to occur, right? This is actually what we're generally after in statistics, is to construct something like this. Because this tells us not only what's most likely, it tells us how sure we are about where a range of a value will fall. This is how we quantify uncertainty, which we'll get to next week. Not next week, week after next. No, next week, whatever. We're getting toward the end. Okay, so special features of the normal. Are we feeling okay about the probability mass? The CDF is just the integral of it. This is the one I really want us to understand well. We're feeling okay about this? So the probability, what's greater on the green? The probability of observing a -4 or the probability of observing a 2? The 2, right? It's higher on the curve, right? So the bar at -5 is lower than the bar at 2.5, right? So we have less chance of observing it there. That's what we can read these as, right? There's more variability in the green curves than there is in the red curve, meaning if we're drawing from a variable that has a distribution that it looks like the red curve, the values are going to be pretty compact, around 0. If we're drawing from a random variable that follows a 0-2 normal, they're going to be more spread out. Okay, so one reason we see normal variables all over the place in statistics. And one reason for that is that there's this kind of neat characteristic that when you add together lots of other random variables from many different kinds of distributions, they tend to follow an approximately normal distribution. So there's a lot of things in nature that follow normal distributions. And lots of random events summed together, like if we sum many binomial random variables together, the distribution of that sum will be approximately normal. And so that's like, okay, well, that's fine, but why should I care about that? Well, if we think about a natural process occurs often as a result of lots of different random processes, right? Some of which we can observe, some of which we can't. But if we know that the sum of lots of different random events is approximately normal, we can model the likelihood of a very complex process without understanding every piece of random event that led into that event, right? We can summarize uncertainty without having a full theoretical grasp on what caused the process to occur. That's powerful. Another special feature of it is, again, the kind of movement. We notice this. So for X, distributed normal mu sigma squared, this is the second bullet, Z equals X plus C. That is adding some constant C to a normal, just moves the mean, right? So then we have a mean of mu plus C. And we saw that with our blue curve, right? If we have the normal variable X distributed mu, X distributed 0, 1, X follows a normal distribution with mean 0, standard deviation 1. If we add 2 to that normal random variable, all we've done is move the mean by 2. The rest of the shape remains the same. So we can move normal distributions by adding any constant to them. We add a constant to it, the shape remains the same, the location changes. All we're doing is changing the mean. So you can add a constant to a normal, and its new distribution will be Z distributed mu plus C sigma squared, where C is just that constant that moved it left or right. Z equals C times X, where X is normal mu sigma squared, is equal to Z is normal C mu C sigma, right? So we can just multiply. If we want to multiply a normal distribution by a constant, we just multiply the mean and the standard deviation by the constant. So both the location and the shape change when we multiply a normal. Z-scores of a normal are 0, 1. That's weird. We'll get to it in just a second. But the Z-scores, remember we talked about Z-scores as we subtract the mean and divide by the standard deviation. So we can always convert a normal into a 0, 1 normal by subtracting out the mean and dividing by the standard deviation. That is, if I have, we can take those two rules before to say X is normal 5, 2. But let's say I want to convert that into a Z-score. We'll say Z then is equal to X minus 5 divided by 2. And we can convert that then to a normal that has mean 0, standard deviation 1. Right, we can follow this addition and subtraction rule to then create a new distribution, 0, 1, that we'll call a Z distribution. So we can convert any normal to a 0, 1 normal by subtracting the mean and dividing by the standard deviation for every single observation of the data. That'll convert it to a 0, 1. And a 0, 1, you're like, well, okay, that's cool. Why would we do that? It makes inference so much easier when we work on a 0, 1. Because normals have a lot of properties that are easiest to interpret on a 0, 1 space. So here's area under the curve again. 50% of the mass of the normal falls in that blue area. Yeah? We feel good about that because it's symmetric. So we know that 50% probability, we have 50% probability of observing something less than or equal to 0, right? Where the height of the blue area at each point represents the relative probability of observing that exact value. I say relative because, of course, the probability of observing exactly a 2 is infinitesimal, right? Because these are real numbers, right? It's a super small probability that we'll observe exactly one number in a real number space, but it's proportional to 0.5, right? If that didn't make sense, don't worry about it. But on a real number, right, as we kind of went back to our, well, let's just draw from a normal and see. So our norm, I should expect on a normal 0, 1 to observe something around the mean about 50% of the time, right? So let's draw our norm. I'm going to draw 1, the mean equals 0, SD equals 1. I got a minus 0.09415. I could probably run this 100,000 times and never observe exactly a 0, right? But I'll observe a whole lot of things that are very close to 0. Let's see. Let's try 10 and see what we get. Nothing exactly 0, right? Because on a real number space, we have an infinite number of possible numbers. The likelihood of observing any one particular number is vanishingly small. But we can predict how likely we are to observe things within ranges. Okay. So this is the cumulative density, right? We have a 50% mass going up to 0. And then we can turn that, we can turn effectively the size of this area as it grows. We can treat this as a number, right? The height of the blue over time, right? As a number, and we can convert that to our CDF, right? So that area now takes on a different curve, and we get to 0.5 when X is equal to 0, right? So we kind of convert the total area of that blue into a straight line. That's what the integral does. That's what the area under the curve does, is it converts that area into a straight line. Or not a straight line, but into a line. A curve, rather. Okay, so here, how much probability are we gonna, what's the question that this shaded area answers? What does this shaded area tell us? Right. Well, we don't know that yet. We'll come to that in a second. But this blue area tells us how likely we are to observe an event less than or equal to 1, -1. And let's read that off on our CDF. We can compute what that actual area is under the curve by taking the integral, and we obtain about a 0.18, something like that. 0.15, somewhere in that range. You're never actually going to compute the integral. You're going to use functions in R to do it. But you know, that's what the math is underneath the hood. All right, so this goes up as we accrue more area under the curve. Okay, so the z-scores help us understand area under the curve. To obtain a z-score, we subtract the mean and divide by the standard deviation. So for a normal variable, z-scores are distributed z distributed normal 0, 1, as we just discussed. So a z-score of 0 indicates an observation at the mean after we've reshaped a variable, right? We can take our variable distributed normal with a mean of 250 and a standard deviation of 180. We could subtract off 250, divide by 180, and now something with a value of 0 is at the mean, which if we transform it back would be equal to 250, right? So we can go back and forth between z-scores and the observed scale. That's not a big deal. -1, what would that indicate? A z-score of -1. What would -1 on a z-scale indicate? So our unit on z is now, we've divided by sigma, right? So we're on sigma units. And what is sigma? Our standard deviation. So -1 indicates that it is -1 standard deviations below the mean. It's 1 standard deviation below the mean. Right? We've converted it onto a sigma scale. So we're 1 sigma below the mean, sigma being the standard deviation. 2 indicates that we're 2 sigma above the mean. 2 standard deviations above the mean. So let's look at that. Because the normal is symmetric, it has a lot of really cool properties that can help us understand the probability, mass, and the cumulative density have a lot of really cool properties. So for a z distribution, this is a z distribution, a 0, 1 normal. We're going to think about 0, 1 normals a lot. So this is a 0, 1 normal plus or minus 1 standard deviation. So 0, -1, 1. It is a fact that anytime we have a normal 0, 1, 68.3% of the mass of the distribution will fall between -1 and 1 on a normal 0, 1. So anytime we have a normal 0, 1, we have a 68% chance of observing something between -1 and 1. Now, by contrast, what this means is for any normal, we have a probability of observing, so we'll call it mu -1 SD less than or equal to x less than or equal to mu +1 SD is equal to 0.68. Right? Doesn't matter what the mean and standard deviation are. If we go 1 standard deviation above the mean and 1 standard deviation below the mean on a normal, we have a 68% chance of observing about 1 random value drawn from a normal, 68% chance it'll fall within 1 standard deviation of the mean. Every time. Any normal, 68% chance. Now we work with the 0, 1 just because it's easier to talk about -1 to +1. If our standard deviation was like 12.6, and our mean was like 22, talking about 22 plus or minus 12.6 gets more complicated, right? But beautiful thing about the normal, we always have a 68% chance of drawing something within one standard deviation of the mean if we draw one random number. We have a 95% chance of drawing something within two standard deviations of the mean. So if we go out to two standard deviations, mu plus or minus 2 SD, mu plus or minus 2 sigma, and we draw one random number, there's a 95% chance that any value we draw will fall in that range. For any normal distribution, we have a 95% chance of drawing a single number. If we draw one number, there's a 95% chance it will fall within plus or minus 2 standard deviations. Or 95% of the probability mass falls within 2 standard deviations on either side of the mean. We're cutting the tails out here. We're ignoring the tails. And why might we do that? These tails have the lowest likelihood of occurring, right? They have the least probability covering more space, right? These points have the lowest kind of portion of the distribution. So even though we could draw a 95% interval that goes from here to say here, it's less efficient, right? Well, think about what we could draw 95% intervals of the distribution in different ways. We could move it around, but the smallest one in terms of X, how much X space we cover, will always be symmetric about the mean, right? That is, we'll start at the mean and we'll add a constant to either side of the mean. That's going to be the smallest interval possible in terms of X. We could obtain other intervals that cover the same probability mass, but they would be larger in X. It would be wider. We can think about this as the narrowest possible 95% interval. We'll talk more about this as we go. Now, another feature of normal. So we did one standard deviation, 68%. 68% of the mass is within 1 SD. 95% is within 2 SD. 99.7% is within 3 SD. So virtually all of the mass of the normal is within 3 standard deviations of the mean. And again, this is true for every single normal distribution. So events that are more than 3 standard deviations away from the mean, are they likely to occur or unlikely to occur? Is a 4 likely? No, right? Is an event that is a 3.5 standard deviation away from the mean likely? No, it's very unlikely. So if we draw a single random variable from a normal, we're virtually guaranteed that it will fall within 3 standard deviations of the mean. We will observe events outside of that, very rarely. Most of the time we won't though. Okay, so these visuals of how the probability density covers different areas in the mean will be the foundation for things like confidence intervals, will be the foundation for things like significance tests. As we think about regression, we're going to extend this logic of thinking about the predictable nature of a normal distribution to think about how our error terms are distributed, right? This is how we're going to use the normal, is we're going to think about the normal as a way to model our errors in the context of regression. And once we do that, we can talk about how certain we are about our estimate of the mean by using the properties of the normal distribution. Okay, so here are some useful probability functions in R. We have d norm, which is the probability density function. So the probability density of x equals 0 for a 0, 1 normal is about a 0.4. That's going to be the highest probability on that curve. Cumulative density, we use p norm. So if I ask what's the cumulative probability of observing a 0 with a 0, 1, it's 0.5. So p norm will return out the cumulative probability of any value. R norm will draw random values. So 1.2, I just drew 1. The CDF for a given probability, I can use Q norm to do a quantile. So I can ask, what is the cumulative likelihood of observing a 0.75, and it's 67.5. Let's take 5 for a second. When we come back, I have a few more things I want to work through today, but we went a little longer than I intended before break. So it's 11:27. Let's say 11:35. We'll come back. So 8 minutes. But and I guess kind of for my personal kind of statistical journey, for how I kind of learned these things, it took a long time for me to really get my head around thinking in terms of probability distributions. But once you can think in terms of an event as a distribution of possible values, right? So like anytime I see something that occurs, I can think about how likely, what the likely range of things are to occur once I know some basic statistics about. Once you can start to think about uncertainty as a real property of the world, right? Not just as something that we're describing as random, but as something that tells us how events occur and what the likely values they are to occur within. I think it really can change how you think about the world in a way that's useful. And I find that there's kind of this moment that happens that you flip and start thinking in terms of probability to understand how events occur. And that's kind of a good sign that your intuition has become a bit more statistical, right? Once you can kind of start seeing probability in the world, I think it becomes more useful. But probability distributions for me are a really key part of understanding how that works, right? Is kind of seeing that an event didn't just have one possible outcome, it had this range of possible outcomes, and this is the one that happened, right? Okay, so let's do a few more things. We can talk about the expectation of a random variable. The expectation of a random variable, E of X. So if you see the E operator in statistics, that means expectation, and that will always be equal to the mean of a random variable. So the expectation of X will always be equal to the mean. That, and another way of thinking about that is if I just tell you what is the most likely value, if you had to make one guess about the value of a random variable, the best guess you could always make would be the mean, right? That's the most likely value on just about any probability distribution. Sometimes the expectation is not exactly equal to the mean, but the most likely value is not always exactly equal to the mean. But so the expectation is the mean of a random variable. Now, do not confuse E of X and X bar. What does X bar indicate? Sample mean. So X bar is the mean of some realizations of a random variable, some data that we've observed. Now, data are just a finite number of possible observations from some random variable, right? E of X is equal to mu. X bar approaches mu as n approaches infinity, right? But X bar is not equal to mu. Our sample mean at best is approximately equal to the expected value of a random variable, right? Or mu, the actual parameter. So here we're distinguishing between a statistic, X bar, that is something we compute from the data, and a parameter, mu, which is unknown, right? We don't know statistical parameters generally, unless we're simulating, right? Unless we're building a model and we're controlling the environment. But in the real world, we never actually know exactly what mu is. But we're trying to estimate it using statistics, things we can observe from data, like X bar, right? So we don't necessarily know what the exact mean of a random variable will be. We can get close to it by observing X bar from the data. So for a discrete variable, the expectation is the sum of all values of X, weighted by their probability, given by the PDFX. So in this case, when we say, it's actually just, so we can typically think about computing a mean as the sum of X for X of I, for I equals 0 to n over can sum up all possible values of I and divide by the number of observations. For a discrete value, we can modify that by summing up all values of x sub I times the probability of x sub I divided by n, times the probability mass of observing that particular value. So we could obtain the mean of it using effectively a weighted average, where we weight by the probability of observing that value. F of x here just indicates the PDF for our function, right? So x times the function of x. I'm sorry, we don't need n anymore. N is implicit once we're multiplying by the probability. So for a continuous variable, we could just take the integral x times the PDF, right? X times the probability of the event at the value x, integrating from negative infinity to infinity. This will give us the average, the expectation. So we have the kind of, this is just a different way to define an average. We could think of it either as the sum of all possible values divided by n, or the sum of all possible values times the probability of observing each of those values. They'll give us the same thing. The variance and standard deviation of a random variable, right? Standard deviation we've already seen. 1 over n times the sum of all deviations from the mean, right? How far is xi from x bar? Remember, we square it to keep it all positive, so negative and positive errors don't cancel each other. And then we take the square root to keep it on the positive scale, but to remove the quadratic, right? To get it back to a linear form, to remove that quadratic, but keep it positive, right? So to square something and then take the square root of it, we'll take the absolute value. Okay, the sample variance is just the square of the standard deviation. For a random variable x, sometimes you'll see these formulations. I'm just kind of walking through some definitions that I want you to see from statistics, but I won't ask you to do too much work with these. For a random variable x, we can define the variance via the expectation instead of the sample mean. So another way we can express the variance, right? So we could remove the square root. We could express the variance as one over n sum star squared n. I'm sorry. Over n. So that's the variance, right? So we can also write sigma squared in terms of the expectation operator. So we can write it as the expected value of x minus e of x squared. That's a bit of a funky way to think about it, but what we're saying is this is mu, right? So we're saying x minus mu, which looks pretty similar to what's right here, right? Squared. And what's the average value of x minus mu squared? Which is effectively the same thing that we're computing here, right? We're just rewriting it in terms of the expectation operator instead of traditional algebra. But those two things will give us the same value, right? Obviously, without the square root in this case. We could put a square root around this, and then we would have the standard deviation. Okay, so let's talk about a couple theorems that are going to be really important to us. These are called large sample or asymptotic theorems, and we're talking about the law of large numbers and the central limit theorem here. And these are really critical to statistics. So as a sample draws from a random variable, as the number of samples increases, x bar approaches mu. X bar approaches the expectation. So as our sample size increases, our sample average converges to the expected value of the random variable, the unknown expected value of the random variable. So for a very large n, our sample mean is approximately equal to the population parameter mu, or the expectation of x, right? So let me just, going around a lot of terminology, let me just be very clear. U equals E of x equals population mean x bar is the sample average. And this is unknown. This is estimated from data. One of those things is unknown. We don't actually ever know with certainty what the population mean is, but we can obtain precise estimates of a sample average from our data. And by the law of large numbers, we know that as our sample size increases, our sample mean converges to the true population parameter, the expectation of x. This is the law of large numbers. So we can test this, fortunately, right? Because it sounds like, okay, why should I trust if that happens? This is the entire rationale between Monte Carlo simulation. But let's test it. So to test the law of large numbers, we're going to draw from a binomial variable with different sample sizes. So we expect that x bar should converge to the expectation as the sample size increases. And remember, we can know the population parameters when we simulate because we're fixing that within the computer. In the real world, we never know exactly what they are. But here, we're going to say that we have a binomial with a 30% chance of success for each trial, with 10 trials in each draw. So this is going to take on values between what? Each draw of the binomial can take on values between what? 0 and 10. And the average should be what? 3. Because the probability is 0.3. So the expected value for a binomial for a binomial distributed with NP, that is n trials, p probability, the expected value is n times p. Right, so here, 0.3 times 10, 3 should be the average. And we're going to draw 10,000 simulations. So effectively, what I'm going to do is I'm going to use this. I'm going to use a loop. And a loop I've introduced before, but they're kind of funky, but they're really useful for simulation. So first, I just want to show you kind of what 1,000 draws from this will look like. I guess I'm going to show that next slide. So first, x is going to be 10,000 draws from a random binomial with p.3 size 10. So it's going to be 10,000 draws of 10, right? We're going to create a output data frame where I just want to compute x bar for a bunch of different sample sizes. I want to start my sample size at 1, and I want to increase my sample size up to 10,000, or the number of times I'm going to run this, right? The number of draws from this binomial I'm going to take. So what do we expect will happen to x bar as n increases? X bar should converge to 0.3, right? As n increases. So we're going to create an empty data frame that's going to have two variables, n and x bar, where n is going to be every integer between 1 and 10,000, or 100,000 rather. So it's going to be 100,000 rows, and it's going to have a column called x bar that I'm initializing as empty, but we're going to store values in that in our loop. So I'm going to go over, I'm going to create an index counter called I that's going to take on every value between 1 and sims, and it's going to go one at a time. First time, it's going to store in out the value of x bar for I. That'll be 1 in the first iteration. Will just be the mean, right? The sum of whatever I drew for this sample. right? I'm not resampling each time. I've already drawn 10,000, but I can then sample from that. Or I can take the first 10 rows, the first 100 rows, first 1,000 rows, and treat that as independent samples. Okay, you could use cumulative sum, but this works. So let's see what happens. When n is small, my estimate for the mean starts off at 5, goes down to 4.2, right? Sometimes goes down below 3, but it doesn't take very many trials. You can see there's a dip here, but it doesn't take very many trials until it levels out at exactly 3.0. Right? The law of large numbers tells us that as n increases, x bar will converge to the expectation of x. And in this case, it does so after, maybe 1,000 or so iterations. It gets pretty close. For under that, it's not especially close, right? We can be quite far off for small numbers of iterations. So we can think about the distance between this dotted line and this kind of moving bar as being our error in estimation, our simulation error. How far away were we from the population? How far away were we from the expectation of x? Here, we were 2 points off. Here, we're like 0.2 points off. But by the time we get to 25,000, we are very, very close. This is the law of large numbers. As my sample size increases, the sample mean converges to the true value of the population mean. So if we want to know the truth, increase your sample size. Assuming IID, right? Assuming random sample. But that's not guaranteed for just collecting 1,000 people off the street and saying, now I've got a sample that I can compute the mean from. We have to still consider kind of sampling. But as our sample size increases, we converge to the population mean. Questions about how this works? We can kind of let's maybe illustrate it. Let's not. We've left this. Okay. The central limit theorem is another one we're going to use a lot. Similar to the law of large numbers, as n increases, the distribution of the sample mean approaches a normal distribution. Now, this is weird. Our sample mean here, x bar, follows a distribution. We can think of the uncertainty we have and how far away x bar is from mu as itself following a probability distribution. Our error has a probability distribution. And as n increases, the shape of that distribution of our errors becomes approximately normal. So for larger n's, our errors in terms of the difference between our sample mean and the population mean, our error terms become normally distributed with a sufficiently large n. That is, I can tell you the range of likely errors if my n is big enough. I can tell you how far off my guess should be from the population mean with a sample mean computed with a sufficiently large n. That's powerful. So we end up with what's called a sampling distribution of a parameter. We end up with a distribution from which possible values of the sample mean could have arisen. And it's going to be centered around the population, right? So let's think about this. It's a bit tricky. This is the trickiest part. Sampling distributions are weird, but they're really important. We're kind of going from one level of probability to 2 levels of probability. But think of it like this. Our sampling distribution for x bar is centered on mu, right? Assuming we have a simple random sample, right? Assuming there's no bias in what we're drawing, our sample average will be centered around the true average, right? Everyone accepts that if we have a good random sample. We should have as much likelihood of being wrong in a positive direction as we do wrong in a negative direction, right? It's unbiased. So what we get, though, is for a small sample size, our error terms could be distributed something like this. So what this is the distribution of possible values of X bar under a small sample size case. So let's think we run our trial. Let's say we sample 10 individuals and ask what their height is, right? And then we compute the mean for those 10 individuals and we drop the points. And we do it again and we drop the points. And we do it again, we drop the point. We do it again, we drop the point. Point, 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 point. The density of those points indicates how high the curve should be at that point. We can think of this as a histogram, right? The more points we have in a particular area, the higher we want that to go. So we're getting a few points out here, a lot of points in here. And all of these are realizations of a sample mean from the possible values we could have observed for a population from a population average, right? So the population average determines the location of where those values should be centered around, and the standard deviation of it determines how spread out it is. And that standard deviation is a function of our sample size. So what we get, let's say this is our, well, we'll kind of draw these smaller. So we'll say n equals 10, u equals 0. This is our, let's say that's our small sample. This is the distribution of X bar for a small sample, right? It can take on a pretty good range of values, but as n equals 100, if u still equals 10, we're going to have the same location. But now we're going to have a smaller distribution for a possible value for X bar. Now, if n equals 1000, u equals 10, we're going to have a much smaller range. The width of the distribution, the spread of the distribution decreases as our sample size increases. So the possible range of errors in our sample mean decreases relative to the true value of the population mean as n increases. And it follows a normal distribution. The central limit theorem tells us that for a sufficiently large n, our errors, which we could think of as the true mean minus the sample mean, follow a normal distribution. Our sample means are drawn from a normal distribution. That's called the sampling distribution of the mean. Any one particular set of observations we go out and collect is going to be different from the population mean by some amount, right? But the width of that error will be determined by how big our sample is. This is hard. This is confusing, but we're going to keep coming back to it. The central limit theorem underlies the logic of significance testing and the logic of confidence intervals. This is how we're going to do that. We're going to use this assumption that there's a fixed distribution from which samples could be drawn, sample averages could be drawn, that's centered around the mean to estimate possible ranges. Okay. So this relationship holds for a lot of distributions, Bernoulli's, binomials, normals, and others. That is the normal, the error terms, or the sampling distribution of the mean will follow a normal for large n samples, right? For not just a normal variable, but also for a Bernoulli variable, right? That is, if I want to know what the probability of flipping heads on a coin is, and I do 10 coin flips 1,000 times, the distribution of those sample means will follow a normal distribution. Those sample means of what is the probability on each set of flips that could take on values of 0 heads, 10 heads, but those are going to be rare, right? We saw that kind of with the binomial. Looks like it's taken on a normal shape, doesn't it? Roughly. Now, if we increase, now that's just for the outcome itself, but if the mean was our statistic of interest and not the actual outcome, so we have 0, 1, 2, 3, 4, 5 here, but what if we were interested in computing X bar instead of X? We would actually end up with a normal curve centered around 2.5, right? For a large number of repetitions of this experiment. The distribution of the sample mean would follow a normal distribution. The possible range of means we could have observed when we repeat the experiment follows a normal. If that still doesn't make sense, don't worry, it's tricky. And we're going to keep repeating this over and over again for the rest of the semester. And I will tell you that people typically badly misinterpret the central limit theorem when they interpret confidence intervals. This is the foundation of the logic of how we do inference in statistics, and it's really easy to get wrong. Okay. So if our samples are independent and each observation within the sample is IID, IID again, independent, identically distributed, it means one observation doesn't depend on any other observation, and they all follow the same probability distribution. The distribution of z-scores of sample means converges to normal 0, 1. So that means we can shift everything onto a normal 0, 1 space, which is easier to work with, right? Because we know, for example, on a normal 0, 1, that if I have plus or minus 3 standard deviations from the mean, I've got 99.7% of the probability mass. That's super handy, right? So working on that z distribution can make a lot of things in terms of statistical inference really easy. So it's good that we can always kind of go back to that. Okay. So at heart, what the central limit theorem does is it allows us to make statements about how certain we are about something we don't know based on something we do know. How certain am I about this thing that I don't know that I'm interested in based on what I observed? That's what we're after. So here's some more Monte Carlo simulations. I'm not going to walk through the code on this, but here's a 10 sample binomial. And we're converting the means into z-scores. And we can see, so what I've done here is I'm going to compute the mean of a binomial with size 10, with size 100, with size 1,000, with size 100,000 for different sizes. And the distribution of the sample mean will follow a normal distribution as we do this. And that's for binomials, right? These take on values between 0 and 10, 0 and 100, 0 and 1,000, 0 and 100,000. So this is our 10 trial binomial. This is where n equals 10. And so we can see these are the actual averages we obtained over 10 trials. And then I superimposed a normal curve over it. For 100 trials, this is the distribution of sample means that we observed, expressed as z-scores, right? So I converted the actual, the real mean for that would be NP, right? And our binomial here was P is equal to 0.7, N is equal to 10, right? So this should be, the expectation here should be what? 7 NP is the expectation of a binomial. So 10 times 0.7, 7 should be the expectation, but I'm going to convert it into a z-score just to make our life a little easier. So this is our 100 sample z-score. And what I've done is I've drawn a lot of different 10 classroom sizes. I've done it 100 times. These are all of the different means that I've observed expressed as z-scores. I subtracted 7 and I divided by the standard deviation. Okay. And we can see that the shape of this histogram It's not quite normal yet. But we're still at 100. That's relatively small. Let's go up to 1,000. Now the shape of my distribution of sample means, right? These are all the means that I observed from my binomial trials, starts to look more and more normal. When I go up to 100,000, it looks darn near normal, right? So I'm sorry, this is 10,000. So this is a plot of 10,000 sample means, again, of binomial trials where I have 10 draws with a probability of 0.7, right? So each of these could have a value between, for a mean that ranges between, -3 and +3. But what we can say is that our sample means will always fall 95% of the time within ±2 standard deviations of the true mean, right? This is what the central limit theorem allows us to say, is that if we take a single draw of the data, if we take a single sample here, so let's do R binom 1, E equals P, size equals N. We had a 95% chance of that being within ±2 standard deviations of 7. If we do it again, we have another 95% chance of it being within ±2 standard deviations of 7. Right, we could keep doing this over and over. Standard deviation of a binomial is defined as, I think, P over 1 minus P times N. I forget the exact definition, but we could define the standard deviation of a binomial. Anyway, what this tells us is it gives us a sort of range for where we expect the sample mean to be, right? So if we take 10 draws, sorry, I misinterpreted that. It's not that we have a 95% chance of one draw being within ±2. So we have a 95% chance of the mean of a number of draws being within ±2. So let's take a look at that again. Okay, so this is 10 draws, right? So let's take the mean of 10 draws, 6.8, right? Let's take the mean of another 10 draws, 6.4, 6.7, 7.6, 7, 6.5, 6.8, 7, 6.6, 6.2, right? And keep going like this forever. And if we did this 100 times, odds are 95 of them would fall within a two standard deviations of 7. There's a fixed distribution for this mean. It looks like that. Okay, so homework this week will be optional. I've given links to, I don't know if you all have seen Khan Academy before, but it's a kind of useful web-based service that you can do some statistics and probability exercises on. They have 2 units that I think are useful. One is on probability, one is on distributions. So I think working through those is good practice if you want the practice. Also, you could continue working through chapter 3 of the Open Intro to Stats textbook if you want some more practice on probability and distributions. But we'll be coming back to this again when we talk about uncertainty next week. So what we're going to be doing from here on out is talking about how we use the ideas of probability distributions, use the idea of the central limit theorem to make statistical statements about uncertainty. Again, homework optional, so do the review if you like. If you want to take a break, feel free to take a break. Any questions or thoughts?